Example 6.1. Calculate the multipole moments q sub Lm for when 4 charges with magnitude q are placed in x, y, z coordinates such that there are positive charges at a, 0, 0, and 0, a, 0, and negative charges at minus a, 0, 0, and 0 minus a, 0. Solution. We have by definition. See the equation shown. The charge distribution is odd about the origin, can invert sign and have same type of solutions, so q sub Lm will be non-zero only for L times odd. Also, theta equals pi over 2 vector cosine theta equals 0, so q sub Lm will only be non-zero when p sub L to the mth power is an even function of cosine theta. Parity of p sub L to the mth power is -1, raised to the L plus m power, and we know L must be odd so m must be odd. Since, see the next equation. See the equation shown. Equals 2qa to the LTH power times open bracket y sub Lm raised to the asterisk power of pi over 2 comma 0 plus y sub Lm raised to the asterisk power of pi over 2 comma pi over 2 close bracket for L times odd. Now, see the next equation.
See the equation shown. So, see the equation shown. Thus, at lowest order. See the equation shown. Multipole expansion of the energy of a charge distribution in an external field. Consider a localized charge distribution ρ of x in an external potential normal phi of x. Its electrostatic energy is given by equation 6-20.
If normal phi is slowly varying in the region of where normal phi is non-negligible, it can be expanded in a Taylor series around a suitably chosen origin. Equation 6-21. Since E equals negative nabla sign with over it normal phi. Equation 6-22. Since nabla.E equals 0, we can make x squared form traceless. Subtract 1/6 our squared nabla sign with over it.E. Equation 6-23. So, equation 6-24.
From the above result we can see the interactions of various multipoles with the external field that contribute to the potential energy. Thus, there is potential energy from 1. A charge with the external potential. 2. A dipole moment with the electric field, potential gradient. 3. A quadrupole moment with electric field gradient. Etc. Interaction energy between two dipoles p sub 1 and p sub 2 can now be understood from the negative p.E of 0 term with the E of x taken to be due to a dipole, with equation above. Thus, equation 6-25, where n is the unit vector in the direction x sub 1 minus x sub 2, it is assumed x sub 1 is not equal to x sub 2.
Electrostatics with ponderable media. Ponderable media consists sources and materials, such as charges, conductors, dielectrics, etc. Averaging of nabla sign with over it times E sub mic are O equals 0 still yields nabla sign with over it times E equals 0. Thus, the electric field is still derivable from a potential normal phi of x in electrostatics. The dominant molecular multipole interaction with an applied field is the dipole. Therefore, let's focus on the production in a medium of an electric polarization P, denoting a dipole moment per unit volume, given by equation 6-26, where the index is over the various types of molecule. Similarly, the charge density at the macroscopic level is equation 6-27. If we consider no higher macroscopic multipole moment densities than dipole, and consider a small volume element normal triangle V centered at x prime, then we have for the contribution to potential from that volume element. Equation 6-28.
Integrating. Equation 6-29. Using integration by parts and surface terms go to 0. Thus we have equation 6-30. More natural for the ponderable media description is to consider a new effective field D equals E plus 4 pi rho, since we can then write equation 6-31. And effectively have the same mathematical formalism as for bare charge in vacuum. A constitutive relation connecting D and E is necessary before a solution for the electrostatic potential or fields can be obtained. Assume a linear responsive medium, excludes ferroelectrics, which is reasonable for field strengths not too large. Also, assume medium is isotropic, so Equation 6-32.
Where chi sub E is a constant, known as the electric susceptibility. Thus, equation 6-33, where D equals E plus 4 pi x sub E equals 1 plus 4 pi x sub E times E. The constant epsilon of equals 1 plus 4 pi x sub E is called the dielectric constant or relative electric permittivity. Now the divergence equations can be written. Equation 6-34. All problems in the electrically responsive medium are reduced to those of the previous analyses, but with the electric fields produced by charges reduced by a factor of 1 divided by epsilon. Since C equals Q divided by V prime equals Q divided by V divided by epsilon equals epsilon Q divided by V, one immediate consequence is that the capacitance of a capacitor is increased by a factor of epsilon if the empty space between the electrodes is filled with a dielectric with dielectric constant epsilon. If there are different media juxtaposed, we must consider the question of boundary conditions on D and E at the interfaces between media. Equation 6-35.
Equation 6-36. Where n sub 21, the unit normal directed from region 1 to point 2, and sigma is the macroscopic surface charge density on the boundary surface, not including the polarization charge. Let's now consider some boundary value problems with dielectrics. Boundary value problems with dielectrics. Consider the problem of a point charge in a semi-infinite dielectric a distance d, z direction, from a different semi-infinite dielectric. To solve, consider solutions to equations. See the equation shown. See the next equation. See the equation shown. Equation 6-37. Subject to the BC's boundary conditions at z equals 0.
See the next equation. Equation 6-38. Since nabla times E equals 0 everywhere, E is derivable in the usual way from a potential normal phi. Using image method, start by guessing Q prime at a prime, such that, see the equation shown, where sub 1 equals the square root of rho squared plus d minus z squared and r sub 2 equals the square root of rho squared plus d plus z squared. For z is less than 0, simplest assumption is that normal phi sub L equals the fraction with numerator 1 and denominator epsilon sub 2 times the fraction with numerator Q double prime and denominator r sub 1 i.e. Q double prime at A. Normal. See the equation shown. So, Q minus Q prime equals Q double prime. Tangent. See the next equation. So, the fraction with numerator 1 and denominator epsilon sub 1 times Q plus Q prime equals the fraction with numerator 1 and denominator epsilon sub 2 Q double prime. Using Q minus Q prime equals Q double prime and Q plus Q prime equals the fraction with numerator epsilon sub 1 and denominator epsilon sub 2 Q double prime, we then get.
See the next equation. Now, polarization charge density is given by negative nabla sign with over it dot P. Inside either dielectric, P equals chi sub E, so that negative nabla sign with over it dot P equals negative chi sub E nabla sign with over it dot E equals 0, except at Q. At the surface x sub E takes a discontinuous jump, normal triangle chi sub E equals 1 over 4 pi times epsilon sub 1 minus epsilon sub 2, at C equals 0. This implies that there is a polarization surface, charge density on the plane Z equals 0. See the next equation. Since
See the next equation, we can write, see the next equation, thus, see the next equation, and equation 6-39. In the limit epsilon sub 2 is much greater than epsilon sub 1, the dielectric epsilon sub 2 behaves much like a conductor in that the electric field inside it becomes very small, and the surface, charge density, approaches the value appropriate to a conducting surface.
Equation 6-40.